the HL part of energetics, students will be required to calculate the standard enthalpy changes of any reactions given. And there are three methods depending on the information given by the question, okay? So generally, your standard enthalpy change of reaction, okay? When you see the word standard, you need to explain to the student that it means 298 Kelvin and 1 atm. Okay, so standard enthalpy changes of reaction can be calculated in three ways depending on the information given. If you're given the enthalpy change of formation of each of the reactants and products, you can take the sum of the enthalpy change of formation of the products minus the sum of the enthalpy changes of the sum of the enthalpy change of formations of the reactants. Okay, if you're given the enthalpy change of combustion, then you'll take the sum of the enthalpy change of combustions of the reactants and minus it, and minus the sum of the standard enthalpy change of combustions of the products. Okay, if you have given the bond enthalpy, then you'll take the total bonds broken minus sum of bonds formed. Okay? So remember, the method to choose will be based on the information given. It is not based on the equation or the reaction. Sometimes they will give the students a combustion reaction, but for the combustion reactions, they will give the enthalpy change of formation of each of the compounds in the reaction. Then when the student look that it's an enthalpy change of combustion, they tend to use the second method, which is wrong. Because the information given is enthalpy change of formation. So they should use this equation instead of this one. So just explain to your student about that. And also, sometimes the same reaction can be, the enthalpy change of the same reaction can be calculated using two methods. Okay, and then they'll ask, if they're different, then they can ask like, why is it different? And if bond enthalpy is involved, you can explain that bond enthalpy is average value and therefore it is not as accurate as the other two, something like that. Okay? Next, the student will need to learn about Born-Haber cycle. You need to explain, first things first, you need to explain the definition of all the enthalpy changes involved in the Born-Haber cycle. Some they've already learned in previous chapters, for example in chapter 2 about first ionization energy. Then formation and combustion was discussed in the earlier chapters, in the SL chapter of this one. So they need to be able to construct the cycle, like how you can start from the elements, for example is NaCl. Okay, to give an ionic compound, okay, and then Na plus, Cl minus, okay, and then the atomization, okay, gas and atom, okay, and you go up and you get Na plus, gaseous, this is ionization energy, this is atomization. Okay, and then from here you can go down for electron affinity to get this one. Okay, so this is a general cycle. It involves the same steps all the time: formation, atomization, ionization energy, electron affinity, and lattice enthalpy. So you need to explain the definition of each and can give the students examples of each. Okay, and then you need to from here explain that it's actually just a specific cycle of a Hess's law application, and then from here you can deduce that the enthalpy change of formation plus the lattice enthalpy will be equal to the sum of enthalpy change of atomization plus sum of ionization energy plus the sum of electron affinity, and from there you can the question can be modified. You can lose, usually lattice enthalpy we ask, but you can just make any one of them the unknown. Okay. Sometimes there is a minor cycle involved about solution, about dissolving ionic compound in solution. Okay. So from here, you can make it into, okay, and then make it into, okay. So dissolving an ionic compound, okay, this is enthalpy change of solution, this is enthalpy change of hydration, and this is lattice enthalpy. Okay, so lattice enthalpy plus enthalpy change of hydration is equal to the enthalpy change of solution. So this is another cycle that can be asked. The next subtopic in the HL part will be about entropy. So again, you need to define what is entropy. Something like is a degree of disorder. And how if a system gets more and more disorderly, it will have higher and higher entropy. There are two things that the student needs to be able to do from here. One is to predict whether an entropy change, whether a standard entropy change will be positive or negative. Okay, just based on the reaction. So here, the first thing that the students have to look out for is the state of products and reactants. Okay, so students need to know that if the gaseous molecules will have greater entropy than the liquid molecules and then the solid molecules. So if you have more gaseous molecules in the product than the reactant, then you will have an increase in entropy for the reaction. Okay, other minor factors include the type of elements, okay, or compounds, and then the number of moles or the amount. Okay, so generally the more different types you have, the higher the entropy. The more total amount you have, the higher the entropy. Okay, but almost always students only need to look at the state of the products and reactants to predict the change in entropy. Okay, the second thing that the students need to be able to do is to calculate the change in entropy. So change in entropy will be the sum of entropy of the products minus the sum of entropy of the reactants. Okay, you can take note that here we are talking about the enthalpy change, but here we are talking about the absolute entropy value of your compounds. Okay, the last one about spontaneity. You will have to touch on Gibbs free energy and how this can be calculated from the enthalpy change and the entropy change of the reaction. Okay, and you need to be explaining to your student that positive Gibbs free energy will mean that the reaction is non-spontaneous, and negative Gibbs free energy will mean that the reaction is spontaneous. Okay, and other than having to be able to put in the values for this and this to calculate Gibbs free energy, they also need to be able to calculate Gibbs free energy from the sum of Gibbs free energy of products minus reactants. And one more thing that they need to be able to do is to predict whether a reaction will be spontaneous or non-spontaneous based on the sign of enthalpy change and entropy change. Okay, so no values are given, but they will tell you like if you have a positive enthalpy change and negative entropy change, will the reaction be spontaneous at any temperature, or is it at low temperature, or is it at high temperature? So you need to be able to do that. So take note also that the temperature needs to be in Kelvin, and that the delta S is usually given in joule. I mean, joule per kg per mole Kelvin. Okay, while the enthalpy change is usually given in kilojoule per mole. So just remind your student to convert the values. Okay, so the last one, okay, the one that I was talking about, we have a table of delta H and delta S. Can give three energy. So for example, if delta is positive and delta S is negative, you need to be deduced that the delta G will be, you need to be able to deduce that the delta G will be positive at all temperature. Okay, meaning the delta G is, which means the reaction it will be non-spontaneous at all temperature. Also, you need to link between spontaneity and rate. So you need to be able to explain, or rather you need to let your student be aware that if a reaction is spontaneous, doesn't mean it will happen because the rate may be too slow or any other reason. So just need to explain to your students that delta G, or rather whether the delta G can only predict whether the reaction will be spontaneous or not, but it doesn't say anything about how fast it will happen. So whether how fast it will happen will be discussed in the next chapter, which is kinetics.